7, polygons. So we should define what exactly a polygon is. The 5th day people that did chapter 10, I think you know what a polygon is, but to officially give it a definition here, closed plane figure. That has 3 or more sides. Each side is a line segment. That meets only at their endpoints. The endpoints we call the vertices, because they can form angles. So, closed plane figure. Basically, what that means is, I'll give you a couple examples here, but 3 or more sides. 3 or more sides. So, what do we call a 3-sided figure? Triangle. 4-sided figures are quadrilaterals. 5-sided figures are called pentagons, so on and so forth here. So, yeah, a triangle, if I draw a triangle out here, that would be a polygon. You can see I do indeed have, in this case, a 3-sided figure, but I can put little dots on there representing they are line segments that form the figure. If I do a 4-sided figure, and again, these lines can keep going in all directions here. But nevertheless, to form the polygon, it has to be composed of line segments. So a line segment is merely just a portion of a line that has defined endpoints. We talked about lines, rays, line segments, the differences between them all. But to form that polygon there, it has to be composed of line segments. Because if I draw this, 1, 2, 3, well, that's not a polygon. You can go, well, there's 3 sides, maybe. 3 line segments, sure. I agree with you on that, but it's not a closed plane. Closed plane means that there's no just gap. It has, the line segments all have to come together to form the figure. So this is not a polygon here because I have this space here. And again, by definition, it has to be a closed plane figure. So as you can see, everything that they got here, these are all different polygons. There's no limit to how many sides they can have. It can have an infinite number of sides. There's truly no limit. We're not going to get into crazy large polygons here. Not our objective, but as many sides as possible. There's just no limit to them. But what does matter is you see all these are closed. All of them are composed of line segments here. There's 3-sided. There's ones with more than 3 sides. They're all just different types of polygons that have their own classifications here. Inside all polygons, all right? Polygons have interior and exterior angles. Okay? So I'm going to just draw out 2, 3, 4, 5. Draw it like that. So I drew out a 5-sided figure, which we call a pentagon. And we're going to just assume, again, probably not drawing the scale, but we're just going to assume all these angles are the same here. So these angles right here are the interior angles. Right here. Notice there are 5 of them. All right. The interior angles lie inside the polygon. The number of interior angles is the same as the number of vertices. And of course, vertices are basically where the endpoints connect together. So if I made little dots of each one of them here, I could say this is A over here, here's B. They also are the elbow of angles. When we talked about our angles, we had our conversation about vertices. So there are 5 vertices. 1, 2, 3, 4, 5. 5 points on a 5-sided figure, which means it's going to have 5 interior angles. We marked them all. In this case, we're just calling them all congruent here. All right. Exterior angles. All right. These lie outside the polygon. Each exterior angle is adjacent, which means right next to, and for what we're going to be doing here soon, supplementary. What's that mean? Right. So exterior, then I'll bring back our figure here in just a second and we'll look at that. But interior angles are inside the polygon. All right. However many sides there are is how many interior angles there are. The exterior angles are outside. So to find them there, you may have to make a line. And they show right here, like this, you're trying to find this exterior angle here. So they're referencing, in this case here, number 29, number 33, and 34 are asking you to find the measurements of interior angles. 30, 31, and 32, you're being asked to find the measurement of an exterior angle. So what we know to help us figure any of these out here, again, we'll find any information here, but we know that the sum of the interior angle plus the exterior angle always equals 180 degrees. We may not know what F is, and we don't, but we certainly have enough information, and we'll talk about this in just a little bit, to find out any of these interior angles. You're always going to have enough information to find the interior angles, and once you know the interior angle to find the exterior, all you do is subtract that interior angle from 180. Whatever's left over is your measurement of your exterior angle. So if I had right here, basically this angle right here, I'll just call it angle X here. And I'm just going to make up a random number here. Not even 540 divided by 5 is 108. So this would be 108 degrees here, right there. Fuzzy. So I'm telling you that this angle here is 108 degrees, and you should be able to use that information and know, well, this is 108, that's 108, that's 108, and that's 108, because they're all congruent. You know, got those ticks there. All right. So if I said, well, any one of these is 108, they're all 108 because they're all congruent, and I said, well, find the measurement of this right here. What's the measurement of the exterior angle? So I know the interior plus the exterior equals 180 degrees. And I know that the interior angle is 108 degrees. And if I add it to the exterior angle, it will total 180. So then I would just subtract 108 from 180. X would be 72 degrees. The measurement of this would be 72 degrees. Measurement of my exterior angle. Okay? So a couple different things going on here. We're almost done here. Couple more. So let's talk about regular polygons. And they're also called perfect polygons. The book calls them regular. Some people call them perfect polygons. They are one and the same thing though, so I tend to call them perfect polygons. And in the 8th grade book, they call them perfect polygons, but in the 7th grade book, they call them regular polygons. So why they felt it necessary to switch the terminology around from one year to the next, I don't know. But they're interchangeable. They mean the exact same thing here. So a regular polygon or a perfect polygon has congruent sides and angles, period, end of discussion. So if, like what I just tried to reference here, and again, I may not have done a great art job here, but this would be by definition a regular polygon because all 5 sides are marked as congruent here. The book has a little picture here with some more examples here. Right here, they show a regular quadrilateral. This is a square. A regular pentagon. Notice how, again, they have markings here. There's a regular hexagon. There's a regular pentagon. So they're considered perfect or regular because, again, all the angles are the same measurement, all the line segments are the same measurement too. And not all polygons are regular. I mean, if I draw this right here, well, is it a polygon? Well, yeah, it's a polygon. Is it a regular polygon? No, why not? Right, the sides aren't congruent. The angles are all 90 degrees, so we can check that box off. But we can say these sides are congruent, but these sides are not congruent, not regular. So, and again, it can be, I can draw, another 5, here's a 5-sided figure. That is by definition a pentagon. May not look like the pentagon that you know in your head. A pentagon is just a classification of a 5-sided figure. It has nothing to do with it being a perfect, but we're more familiar again with something, well, that's again probably not real accurate. There you go. Here, let's put that. There you go. Usually when you think pentagon, you think that right there, or the building in Washington, D.C., which is a perfect one. Regular one. But as long as it's a 5-sided figure, 1, 2, 3, 4, 5, 5-sided figure, pentagon. Right? It's a pentagon. It's just classified by how many sides it has, not by what it looks like or what you think a pentagon should look like there. So again, we're not getting too deep down the well here about naming and all these things here this year. That's not necessarily our primary objective, but the book has some other information here that I don't really want to go through, to be honest with you. They talk about these diagonal things here. I'm not real worried about that here. That's not something I ask you to do with these diagonals here. They talk about concave and convex polygons. That is also something I don't really want to go through with you guys. It's not that relevant. I'm trying to see, well, the only questions that we should need to skip is 22 and 24. Well, no, and we could find the sum of the interior angles. Right. So we'll show you how to do that in just a moment here. So we don't need to skip anything here, but you don't need to do this drawing diagonals. They don't ask anything about concave or convex polygons here. I'm not going to go through it with you, but if you're looking in the book, you see they have more information about that stuff there. They have more information about these diagonals and how that works. It's just not that important, to be honest with you. So, okay, so why don't we shift over to notes here. I think we got all the definitions we need. I think, again, it says write the meaning of each prefix used to name the polygons, but at least in the hardcover book, there's no information provided on that there. I think either in your workbook or your textbook, though, they have more information on that stuff. Let me check here real quick beforehand. So here's the workbook here. If not, then I won't get too bent out of shape about it here. Okay, the workbook doesn't have anything. Ooh. A hepta?
Yeah.
Hepta is 7. Yeah, I might just write them all out for you real quick then. 1 through 10. I'm just seeing if they got them all in here or not here. Tables. No. No. Doesn't matter. I can just write them all out for you. So, all right, I'll provide you up through 10. Okay? So obviously we start with a 3-sided figure here because there is no such thing. If I just, how do I draw a 1-sided figure? Well, that's impossible. 2-sided figure, I guess it's just a line. That's not a figure. So it starts with 3-sided figure. Back to our definitions. 3 or more sides. So that's where it begins.
I actually got 8.
I'll go through. I'm going to write out 3 through 10 right now for you. So 3-sided figures are called triangles. Most of us know that here. Right. 4-sided figures are called quadrilaterals. And they have further classifications such as rectangles, and squares, and trapezoids. So there's a number of different 4-sided figures. They have their own day in the sun, lesson 9/8 triangles, 9/9 congruent triangles, 9/10 compass. Yeah, when we get to 9/11, we'll talk about all the different types of quadrilaterals. There they all are right there. So we'll go through and talk about them. They have their own day in the sun. 5-sided figure is considered a penta. And again, they're most interested in the prefix here, but they're called pentagons. A 6-sided figure is called a hexagon. Hexagon. A 7-sided figure is called a heptagon. An 8-sided figure is called an octagon. A 9-sided figure is called a nona. N-O-N-A. N-O-N-A. Nonagon. And a 10-sided figure is called a deca. So that's as far as we need to go with this here. So that should give you, if you have all this information written down, and I would write it down because you need to complete this table here. It says number of sides, name it, angles, sides, all that good stuff there to finish this part here. Huh? Well, I haven't gotten that far yet, but yes. Yeah, absolutely. I haven't gotten there yet. So first we're just working on all the names. So this is all general knowledge type stuff here. It would serve you well just to learn this information here and just carry it with you through life. Especially this one, and this one. Those are pretty common ones there. So the other ones not so much, but these three, along with the triangle and quadrilaterals, of course. If you can identify, name a pentagon, a hexagon, and an octagon, there's a lot of tools that have those types of shapes, and they're just commonly used. So a lot of nuts, bolts, and things, and signs, and all that are in one of these three types of shapes here. So these are the big three: the pentagon, the hexagon, and the octagon. 5, 6, and 8. The other ones, 7, 9, and 10, aren't very commonly used. So if you can learn at the minimum these three, that's good information just to have with you in your life. So, okay. Finding missing angles. So they start out with triangles, and then we move into some other types of polygons here. So to find out missing measurements of triangles, all right, it helps to know what the total degree measurement of a triangle is. So what is the total degree measurement of any triangle? How many degrees? Yeah, triangles, 180 degrees, always. What that means is the sum of the three angles, I'll call them 1, 2, and 3. The sum of angle 1 plus the angle 2 plus angle 3 always equals 180 degrees in every triangle known to man. Doesn't matter how big or small or anything. The angles always total 180 degrees. So if I drew, for example, let's say like this right here, and if I just gave you that information here, do I have enough information to know what these missing angle measurements are? If I said, what's the angle of this right here, how could I figure it out?
Divide 180 by 3.
Right, because they're all congruent, right? If this, and this are all the same, I just divide by 3, get an answer of 60 degrees, right? And this is what we call an equilateral triangle, and we'll classify triangles later this chapter here, but all three angles are congruent, all three angles are the same measurement, 60 degrees. What if I put this one out here? I'll just draw that. I'll say this is 86 degrees, and I'll call this 71 degrees, and I said, well, what's that one right there? Do I have enough information?
Is this in our notes?
Yeah.
Subtract 1 from 71.
Well, walk me through it, and what did you get? Max.
71 and then 86. Don't you add add them, and then 180 divided, or 180 minus both of them added together.
Oh, what's 86 plus 71?
It's 157. So
157.
80, that'd be 23.
23 degrees. So this would be, again, don't get bent out of shape that clearly it's not drawn to any right scale here. So, okay. But yeah, it'd be 23 degrees. What about this one right here? If I did it like this. Do I have enough information to figure out what this angle is right here? Okay, you guys figure it out. Pull a stick. What's the measurement of this angle right here?
40.
I'll pull a stick. Walk me through it. Kara.
So you subtract 180, you subtract 180, well, 110 from 180,
Yep.
and then you divide by 2. So that'd be 70 divided by 3.
Right, so I still got 70 degrees, so I know this plus this equals 70. So if I write 70 here, well, that's no good because this obviously isn't 0 degrees, is it? Yeah, it wouldn't even make any sense. I wouldn't have anything left here. But I know these are the same here. So she is exactly right. So the sum of these two, because I subtract what I know, the 110 from the 180, it still leaves me 70 degrees to figure out. But I know these are the same. So same thing that we did up here. When they were all the same, I just took my total divided by the number of congruent sides. So I take my 70, divide it by 2, and 70 divided by 2 is 35. And that tells me that this is 35 degrees. But since this is congruent, I'm not really asking for it, but it has to be 35 degrees as well. 35 plus 35 is 70. 70 plus 110 does equal 180 degrees. So there's always going to be enough information here. If I see and said, well, what's that? Do I have enough information here?
Yes.
What does this mean right here?
90 degrees.
Right, it's a right angle. Right, when I see that box there, such as right there, it lets me know that's a 90 degree angle is formed here. We see it again over in question 33. So that's information we need to know here. So now the question is, what is x here? I know what that symbol means. I know what that tells me. So what am I missing here? Nick,
What's the number?
what's my measurement here?
I mean, the angle is at 40 on top.
Yep, that's 40 degrees up here. Yep.
Okay, so we just gotta do, 40 minus 90, so we got 90.
Yep.
That's just 110? No, that's not. No. It's just 90. And then minus.
Right, and then subtract that other angle I know. So I take 180 minus 90, now I'm at 90. Subtract 40 from that, and that gives me, right, 50 degrees. And of course it makes sense. 50 plus 40 is 90. 90 plus 90, there's all 180. I found them all there. We got it covered here. Life is good. Okay, good with the triangles? Okay. All right, let's talk about some of the polygons here. Okay, some of the polygons that are going on here. So, assume here, here they want the sum of the interior, so we'll talk about that first here. Okay, figure out the sum, and we'll talk about that. So, reference it here. Find the sum of the interior angles of a polygon. And this is formula driven here. I'm going to give you a little formula here. So all you need to do, this is our formula, is you take the number of sides, however many there are, subtract 2, and then multiply by 180. Okay? Whether it's perfect or not perfect has no bearing on anything. So I can take we already know a triangle here, right? We just did a triangle. So how many sides are on a triangle? Triangle. And we already know what the answer is. It's 180, right? So a triangle has 3 sides. So I plug it in there because n is the number of sides of a polygon. We went through not long ago, we went all through 10 sides, so a pentagon has 5 sides, an octagon has 8, so on and so forth here. A triangle has 3. So I plug in the number of sides and subtract 2, and then I take that and multiply times 180. So PEMDAS, of course, tells me you do your parentheses first. What's 3 minus 2? 1 times 180 is 180. So a 4-sided figure, like a square or a rectangle, what's the total degree measurement of that? 360. Right, any 4-sided figure. Square, rectangle, rhombus, doesn't matter. So we'll call that a quadrilateral. We'll test it out one more time. We already know the answer, but that, of course, has 4 sides. So I use my formula. Subtract 2 times 180. Of course, 4 minus 2 is 2 times 180 equals, and there's my 360. So I can use this here. Most people know the triangle and the quadrilateral by heart. You should. But what if I said, I don't want to draw it out here, but what if I said the octagon? The octagon. I'm not going to draw one. And I want to know the total degree measurement of the interior angles. And again, what we're figuring out here is I'm figuring out this plus this plus this. For the quadrilateral, this plus this plus this plus this. So the total degree measurement of all the interior angles. Notice how the more sides it has, the larger the degree measurement's going to be. So the octagon. Walk me through how I would figure this out here. Molly. So how do I set up my formula? So how many sides does the octagon have? I'll go back to your notes. You did the octagon. How many sides does it have? Right, 8-sided figure. So what do I do with that? Where does that go in my formula here? Right, so in my brackets I have 8 minus 2, and then what do I do with that? Times 180. Alright, so let's figure it out now. So now I got all my information in there, so how do I go about and solve this? What do I do first? What's 8 minus 2? 6. And then I multiply that times 180. What's 6 times 180? You can use your calculator. Oh, don't have calculators? Anybody, what's 6 times 180? 1080. Right. So there's the sum of the interior angles of an octagon. And I can do that for any. any size figure, it doesn't matter how many sides it has, to be honest with you. Okay. Last thing I'll show you here, they don't mention it in the homework, but they do in the book here, is when you get to really big figures, they all have names. Everything has a name of some sort here. But usually once you get above 12, they don't name them what they are because the names get crazy long at times here. So say I had a 21-sided figure. All right? And I don't know officially what a 21-sided figure's name is. I can look it up online. But so what they call that, and you can call some of these things, are called n-gons. N-gons, where n just represents the number of sides. So let's just say I had a 21-sided figure. I would call that a 21-gon, like that. That's how it would look, right here, 21-gon. And if I said, what is the sum of the interior angles of this n-gon, in this case a 21-gon, how would I do it?
19 times 180.
Right, I just plug in, same formula, 21 minus 2 times 180. And then that's 19 times 180 is
3,420.
20? Right. So, it doesn't really matter how big the figure is here. Okay, we will finish this at 1:30. I got a couple more things I gotta go through here. That is fine. We'll do the last couple parts here when I see you at 1:30. So just bring your math stuff back with you and we'll finish the lesson.